Continuing on with our exam review, taking a look at problem number 17. This is basically they're giving you the graph of the first derivative, and they're going to ask you to interpret some information about the original function. Now, in reviewing this is really the all about me sheet. First of all, notice that I'm labeling this graph represents the first derivative so that my thinking stays clear as to what I've been given, and they're asking me questions about the original function. Again, review the all about me sheet and make sure you know that inside and out. Question A, on what interval is the original function f increasing? Well, remember, the original function increases when his first derivative is positive. So the first derivative graph is positive here and here. So the original function is increasing from -3 to 1, and then again from 3 to 4. Now notice they did tell me to focus on the closed interval from -4 to 4. The original function is decreasing whenever his first derivative is negative and his first derivative is negative in these two intervals. So the first derivative is decreasing from -4 to -3, and then again from 1 to 3, and it does ask why, and we would say because first derivative is negative, and for where it's increasing, the first derivative is positive. Next question, where does f, the original function, have critical points? Remember, critical values are values that make the first derivative either 0 or undefined, and we can see that the first derivative is 0 at -3, the first derivative is 0 at 1, and the first derivative is 0 at 3. So our critical values would be -3, 1, and 3. Also, you'll notice from the graph, looking at the color coding, at those critical numbers, the first derivative does change signs, so we know that we're going to have some local or relative extrema. Now, a relative maximum, which is the next question, occurs whenever the first derivative changes from positive to negative. Well, we can see that by looking at the color coding of the graph. The first derivative changes from positive to negative at x equal to 1. So there is a local or a relative, remember our sentence, occurs at x equal to 1, and is f, is the name of this function f? Yes, f of 1, because first derivative changes from positive to negative. Now there are two local minimums or relative minimums. There are relative minimums at, we can write it this way just to save a little bit of space, -3, f of -3, and 3, is that right? Yeah, f of 3, because the first derivative changes from negative to positive, meaning that the original function would be changing from decreasing to increasing. Points of inflection. Remember, points of inflection on the original function occur where the first derivative has local max and local mins. So we're looking up here at a local maximum on the graph of the first derivative and a local minimum down here on the graph of the first derivative. So there would be point of inflection at, let's see, what am I estimating that? Like -1.2. So I'll say a point of inflection is at -1.2 f of -1.2, because it does ask me for the points. And then down here, I'm going to call this 2. So the other point of inflection would be 2f of 2. So you can see, hopefully, that you really do need to study that All About Me sheet. Make sure you know all these facts. When is the original function concave up, concave down? Kind of the same idea. Wherever the first derivative is increasing, we are concave up, and wherever the first derivative is decreasing, the original function is concave down. So let me get rid of my colors on here. And I'm going to color code. I'm not going to write it up in the interest of the space that I have at the bottom. So let's go with this orange here. So when is the function concave up? Well, the original function, go back to pen, the original function is concave up from -4 to, I think we called it -1.2, and then it would go to concave down from -1.2 to 2, and then the original function would go back concave up from 2 to 4 because of the increasing and decreasing of the first derivative. Next problem. The amazing Fortini is walking on a tightrope. His velocity is shown. So what we have here, we want to keep in mind that this is a velocity graph, so I label it that way. Question A, when does the tightrope walker change directions? Now you got to be careful. It's not just when the velocity is 0. The velocity is 0 here and here and here, but it says change direction. So what we're looking for is we want to see velocity change signs. And the only time the velocity changes signs is at, these off, 1, 2, 3, 4, 5, 6, 7. The 7 goes here. At t equal to 7. Because velocity changes signs. When is his speed? Now there are two ways to calculate the speed. Remember that speed, very important, is not acceleration. It's the absolute value of velocity. We already have a velocity graph. So what you're looking for, there are two ways to analyze it. You're looking for when the velocity is the furthest away from the x-axis. So we're, in other words, the highest velocity in the positive region is at 3, and in the negative region it's down here like 3.5. So really you're comparing the max and the min, and in this case he's going faster at this time than he is at this time up here. So the maximum velocity, when is his greatest speed? Not what is it, when is it occurs at 10 seconds. Now the other way that you can do that, I don't know if you remember this from the past, since speed is the absolute value of velocity, you can just take the absolute value of this graph and flip that up, and you can see the same thing that we did the other way. Part C, when is his acceleration? Acceleration is slope of velocity. So in other words, they're really saying, what is the slope of this graph at 6 seconds? Let me get rid of some of the stuff on here. Alright, so I'm focusing on what's happening at 6 seconds, which is right here. Now notice that 6 seconds is on this linear segment. So all they're really asking me to calculate is the slope of that little linear segment, and it looks to me like we're rising 3 up, and we're going to go back to the left 2, so we would have 3 over -2, which is -1.5. What are our units here? Feet per second squared. Yes, seconds. Feet per second squared. That would be his acceleration. And again, all I did was calculate the slope of this segment right here, which was a rise of 3 and a run to the left 2. Number 19, chemicals from a storage tank are leaking into a pond. The rate of flow is measured at intervals and is recorded in the table below. So R of T is in gallons per hour, so this already is a rate. And T, of course, is the time. And this R of T is in gallons per hour, which they're telling us in the problem. What is the average rate of flow during the first 8 seconds? The average rate of flow. Okay, this problem, I remember, has a flaw in it. And the reason it does, they're asking us for the average rate of flow, but they're already giving us a rate right here. So let's get rid of problem number 19. I'll try to remember to tell you to get rid of it before you actually look at it. But every year we come across this, and every year I forget to tell you that number 19 has some issues. Finally, number 20, the figure below shows the graph of f prime. So in other words, you're trying to identify the original, the first, and the second. So we want to know the original function, the first derivative, and the second derivative. This one's really easy because you can see that you have a cubic equation, which is letter B. You have a quadratic, which is A, and a line, which is C. So it only has to make sense that the cubic would be the original function. The first derivative of a cubic by the power rule would be a quadratic, A, and the derivative of a quadratic would be a linear, C. But if the graph is a little bit more complicated, what you want to do is you want to identify places on the graph where you know that the derivative is 0. So if you look at the cubic equation, the derivative is 0 at this local max and local min. And if you go down, you can see that the graph of the quadratic intersects the x-axis at 0, intersects the x-axis at 0, just verifying that, yeah, that has to be the derivative. All right, we're going to pick up with this in the next video. So I'll see you then.